Hello. In this session, I will talk about the sequences. Let's start with a brief definition of the sequence. We may say that the sequence is basically a list of numbers written in a definite order. A sub 1, comma, A sub 2, comma, A sub 3, comma, and so on. As we can see, first of all, is the list of numbers. And respectively, the A sub 1 is called the first term, A sub 2 is called the second term, and so on. A sub n is called the nth term, the general term, yes? N is called an index. And n, as we can see, is a counting numbers. That means n belongs to natural numbers. Counting numbers are the natural numbers, and they are basically a positive integer. 1, 2, 3, 4, like that's how we count items. That means we will have 1, 2, 3, 4, 5, and so on. Okay, talking about the general term A sub n, yes, we can see A sub n, we may also be able to define in the general way the next term, yes, like the successor of A sub n, which will be called A sub n plus 1. Because n is a positive integer, we jumping by 1, by a positive integer, okay? And then the next one will be A sub n plus 2, A sub n plus 3, and so on. Also, we may need to define a term which is before A sub n. It will be A sub n minus 1, A sub n minus 2. Okay, because we can see 4. 4 minus 1 is 3. 3. The next one is 3 plus 1. So we can operate with any natural number. Okay, and now it's again, sequence is a list of numbers, and we probably know with a pattern. That means these terms are connected with the pattern, and that pattern will be described by the general formula, which A sub n will provide this. And this pattern also allowed us to predict the subsequent terms, the next terms, the following terms. And we always, in this session, this class, we always talking about the infinite sequences, assuming that the pattern will continue. If we find the pattern from a couple of first term, and even if we have a general formula, that's of course obvious, then we always know that the pattern continues. And now we may have a couple of different types of the sequence, or I can say types of the patterns. We may have the arithmetic sequence, geometric sequence, quadratic sequence, triangular number sequence, Fibonacci sequence, okay, and many different ones. But that's some of them. And we later in this session, in this topic, let's say in this section, we will find the examples of those, okay? I mean the formulas, but let's see. Okay, that's what we know. We know what is the sequence, a list of numbers. So now let's look at this. Oh. Okay, that means now we know that we may have that pattern. This pattern can be represented by the formula A sub n, the corresponding number A sub n. Also, because A sub n will be the formula, we can also say that the sequence is a function whose domain is the positive set of the positive integers. That means basically when we have a function f of x, yes, we usually have a formula, like let's say 2 to the power of x. Now we will have, we may say that corresponding function for the f of x is f of n, 2 to the power of n. And we're not really using f of n description for the sequence. We will say a sub n is defined as a 2 to the power of n. Okay, and now before we look deeper in these formulas, let's look at that's what this means. Let's list the terms. That means 2 to the power of because this formula, yes, is defined only for the natural numbers. 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and so on. We may use this curly bracket sometimes, okay? As we can see, it's just like a discrete numbers. And yes, 2 to the power of n. When we think about 2 to the power of x, we're thinking about a continuous function because x could be any real number. That's we can still call it using this notation. A sub n equals 2 to the power of n. That's the one of the formula of the sequence. The pattern will continue. We can call that this is a function, but only with the domain being a natural numbers. That means let's maybe use this color for the function. 2 to the power of x, we know it's a nice exponential function. It's defined for all of the numbers. But what that means, this is just a graph, but now I will have n and a sub n. And a sub n is defined 2 to the power of n, which will be 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, which maybe let's put the values 2, 4, 8. We know how fast this is growing. But what is my point? My point is to show you that we can call it function, but only like this, discrete. Lots of discontinuities. These dots are representing a sequence. The blue curve is representing a function. And since the dots follow the same path, we may adopt lots of rules, properties, for instance, for the limits, how to compute a limit of the function. We may also think how the sequence behaves as n progress to the infinity. We may adopt these properties, these laws for the limits of the function for the limit of the sequence. Okay, that means just the heads up. Okay, but we can see the blue is the curve, the dots are the sequence, the terms of the sequence. Okay, so we know that we can call it a function. We will have formulas, but not x, n. Okay, that's me. Now let's see. That sequence can be denoted, yes, a sub n, with these curly brackets. We may put the formula inside, or we may put the expanded form, the terms, or we may also have this situation, okay, that we may indicate that we're starting with 1 and always going to the infinity. As I mentioned, we will deal with exclusively with the infinite sequences. If nothing is indicated, like the initial point, we assuming that is 1. Or we may also have a situation that we may start from maybe from 3, okay, maybe from 30, depends where we want to start, but we will always go to the infinity. Or actually even, let's have the formula, we may even start from 0. Okay, I know 0 is not a counting number, but we will include 0. But that's it, no negative numbers. Okay, and now let's look at the formulas. In my following example, I am just showing you how to use the preceding notation, defining notation formula, and just writing down all of the terms. I mean, a couple of the first terms. Okay, that's me. Let's see. All of them are similar. Okay, that's me. Preceding notation, defining formula, and terms of the sequence. Of number 1 is this one. N over n plus 1, we will start from 1 to infinity. Or we can just use a sub n. That means this is like a formula, we can see like a function, yes? And this is just like a preceding notation using that curly brackets specifically for the sequence. Or we may list the terms, yes? The first term is defined for n1 in this situation, for n2, for n3, that means this one is a sub 1, comma, a sub 2, comma, a sub 3, and so on. And this one is the nth term. Okay? We may also, let's maybe put the term a sub n plus 1. Okay? That's what we will do. Instead of n, we will put n plus 1. N, that's mean we will have n plus 1, n plus 1 plus 1, n plus 2. Okay, that's mean that's the next step. successor. Okay, that's an example. Let's look at the second example. Okay, we have n plus 1 over 3 to the power of n, and we have that nice component, negative 1 to the n. Negative 1 to the n becomes 1 if n is even, becomes negative 1 if n is odd. That means we will know that these numbers, because that's the main value, will basically alternate in sign. This is just defining formula like a function, and we can see. And again, we assuming that we did start with 1. Okay, that means a sub 1, a sub 2. And we may see negative, positive, negative, positive. Okay, formula number 3. Example number 3. Interesting, we have square root of n minus 3, and of course, algebraically, we're not allowed to have a negative number for the root, for the even root, and then we have to start with 3. Okay, that's the formula, and is the indication, and that's the terms. And now this interesting thing, let's see, the first term is defined for 3. The second term is defined for 4, correct? For n4, for n5, and so on. But even if this is n equals to 3, because 3 minus 3 is 0, this is still called a sub 1. This is still called a sub 2, a sub 3, and so on. Okay, let me just here, please note, not a sub 1, the first term doesn't mean that has to be defined for n1. Okay, that's really important. If you're taking the notes, I hope you're taking the notes, please write this down. Okay, a sub 2 is defined for n equals to 4, because we have not always the index corresponds to the n value for the formula. Okay, and then we have this one, number 4, trigonometrics, and actually you may also notice we're not starting from 1, we're starting from 0, because for the trigonometrics 0 is quite good. I mean, 0 is important number. Formula, the same thing, and now we can see this is defined for n0, and it's not called a sub 0, a sub 1, the first term, because when we put 0, cosine of 0 is 1, and all of the other values from the unit circle. Okay, that's it. Please, note this. Take the notes along with me. You may pause the video. You may look at the notes later. But try to make this session more interactive. Okay, now, yes, in this example, notice that n doesn't have to start with 1. Okay, and now I will have a couple of exercises. We will do together some of them, and some of them you will do alone. Okay, that's me now. I have a list. Let me maybe add this notation. Oh, okay. Let's say this is a sub n, and we're looking for this formula. Okay, let's just do this. And what we see the numbers. 1, expanded form. We have to find the pattern. Of course, the pattern continues. And what we see? 1, negative 1, 1, negative 1. Okay, and we know because we just have it, is basically negative 1 to the power of n. Too fast. And n starts with 1, because negative 1 to the 1, actually no. That we have to correct this, because if we have to start with 1, yes, then negative 1 to the power of 1 will give me negative number. But we do have the first term positive 1. So what I can do, I can change this for 0. Negative 1 to the 0 will be 1. Negative 1 to the 1 is negative 1. Or if we like to start with 1, then we will put n plus 1. Negative 1 is raised to the power of not n, because negative 1 to the 1 will give us negative 1. We will just add 1. Okay, or be flexible with this, or negative 1 if we would like to start still with 1, I can say n minus 1. Yeah? We have to be careful with minus and the initial point because we don't want to end up with the negative exponent, but n minus 1 is fine, 0. All of them are the same. Yes, you may notice all of them are the same because when we start expanding them, we will get this. Okay, that's please make sure that you know how to find the formula. Okay, that means this one is basically -1 to the n when we're starting with 0. Okay, now another formula. Let's look at this nice numbers. Oh, okay, that means a sub n. That's what is the formula? What we see, you may pause the video and you may actually do it on your own. That will be great. Then the session is really productive for you. Okay, 2, 4, 6, 8. They are just even numbers. And even numbers are always divided by 2. This is just 2n. And we start. Oh, we're starting with, oh, my eraser is not working. We're starting with 1. 2 times 1, 2 times 2, 2 times 3, because that term is defined for n1, for n2, for n3, and this will be called first term, second term, and so on. Okay, 2n, n equals to 1. We may still change, rewrite, starting from 0, but then we have to do, yes, a little bit different formula. But let's just leave it. 2n are the even numbers, okay? Even numbers. Okay, now, you may look at this one. Another numbers, set of the odd numbers, 1, 3, 5, 7. How we can define the odd numbers? They are even number plus 1. Okay, and we may start with, let's think, when I substitute instead of n 0, we will get 1. That's we have to start with 0. Or, let's see, 2n, because when I take the even number and subtract 1, we will also get odd number, correct? Because adding 1 or subtracting 1. 2 times 1 minus 1, it is 1. And then 2 times 2 minus 1 is 3. Okay, that's in both of the formulas works. You may pick which one, but please be confident with changing the index and then respectively changing the formulas. Okay, another example. Okay, maybe this one I can leave it for you. Okay, and then you can check later. I mean, you can pause the video or you can check the notes later. Okay, I have to leave it for you. Find the formula for the general term and let's see what we have. Oh, maybe now, let's do it together. The next one I will leave it for you. And then later you will check the notes. Okay, what we have? We have fractions, we have alternation, positive, negative, positive, negative. So I can definitely say is -1 to the n. We may start with 1 because then will be, no, we can start with, let's start with 1, but let's add 1 because then we're making even the even exponent for the first term and it will be positive. It is positive. Okay, now we have fraction. In the denominator, we see 5, 25, 125, 625, just powers of 5, 5 to the power of n. And on the top is counting numbers, 3, 4, 5, 6, 7, but starting with 3. If n is 1, we have to add 2. Then it will be 3, and then 2 plus 2, 4, 3 plus 2, 5, 4 plus 2, 6, and so on. Okay? Okay, let's do the next example. But this one, okay, this one you can try to do on your own. I did make small typo. We don't need this number. We have 1, 4, 9, 16, 25, 36. That's in please pause the video and find the pattern. Yes, you probably know the pattern, but I will not provide at the moment. You will check the video. Okay, now I mean the formula. Okay, the formula. All of the formulas depends on n. Yes, like a function. Okay, now another pattern. 1, 8, 27, 64, 125. Also, you will try to get the formula. You may pause the video and look at this, yeah, and you will check this later, okay, in the notes. Okay, 2, 4, 8, 16, 32, 64, 128. Another pattern. Please try to find the pattern. Okay, number 8. Number 8, 1, 1/2, 1/4, 1/8, 1/16, 1/32. Okay, also you can try to find the pattern. You can check the notes, or you can ask during the class. And then number 9, 1/2, 1, 1/2, 1/3, 1/4, 1/5, 1/6. Also, that's easy. Okay, really easy. Okay, and now number 10. 1, 2, 6, 24, 120, 720. Okay. Okay, please think this one could be a little bit challenge, but I'm sure you know that formula. Okay, you know that formula. And one more, number 11. Number 11 is difficult. Let's look at these numbers. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on. That means, I don't know, probably looking at this, you can predict. I mean, maybe the question is not, it's a little bit, yes, not accurate. What you can do, you can definitely try to find the pattern and maybe list a couple of more terms, okay? But finding the general formula is actually not possible, because we will not find a formula which depends on n. Yeah, I can maybe write. We will not find for this type of pattern, this type of behavior, okay? As may try to list, I can maybe list one more term. 89, that's what you've got. Okay, let's leave it 89, I think it's 89. Okay, I think if you can find another number, that's really good. You figure out the pattern, but to define in the nice explicit formula, it's not possible. Yeah, that means we will not get this one. And now, because of, like, let's say why, this type of sequence, yeah, is defined in the recursive definition. That means recursive definition means that we don't have explicitly formula in terms of n, we actually defining terms of the sequence, like a sub n, in terms of the other numbers in the sequence. That means, let's see. And one of the really nice sequence that is defined in the recursive way, it's called Fibonacci sequence. Yes, you probably hear, and actually the numbers above, that was Fibonacci sequence. That means, let's see the formula. Because we would like to honor the Fibonacci, then instead of A, we're using F. F sub n equals to F sub n minus 1, yes, one term before A sub n, plus A sub n minus 2. And also, along with the recursive definition, we always have to have provided extra information. That's when we know the first term and the second term. That's when let's try to list first term and the second term. That's given. Okay, this is given, the first term and the second. And now, formula is telling us that if I would like to find the third term, 3 minus 1 is 2, 3 minus 2 is 1. That means I just have to add the first and the second term, 1 plus 1, 2. And then I will continue. I always have to add the last two terms, 3, to get the next term. Okay, that's the definition. 3, 2 plus 3, 5, 3 plus 5, 8, 5 plus 8, 13, 8 plus 13, 21. 21 plus 13, oh, 40, something is wrong. Or maybe 34. Oh yeah, why I'm saying 44? I'm just looking at 13 and 21 is 34, of course. 44, what doesn't, yeah. And then 55, I hope I'm adding, and so on, okay? That's, we can see, that's the definition. And just, yeah, in general, I would like you to know how to deal with the recursive definition, yeah? If we have a formula, I want you to be able to list the terms, but we can see we have to read this differently. And maybe one thing that is not helpful, for instance, if I would like to get like 100 term, the 100th term, then I need the 99th and 98th. That means I really have to list them. I cannot just put 100 to the formula, the explicit formula. That means this is the downside of this. But it's still a formula for this, yes, I would say a little bit complicated pattern. And now let's just maybe spend 1-2 minutes talking about this Fibonacci sequence, because Fibonacci sequence, these numbers, even if they look random, they are not random, they are bound to this formula, but we can find them everywhere. Nature, humans, art, music. Some artists, they're creating something and they probably not even thinking that they follow these numbers, these ratios, that pattern. Some of them maybe they know, yes, especially for some like architecture, they will compute, because everything what is like nice, let's say nice, beautiful, will always follow that ratios. Yeah? Because it's also interesting thing when you take the term f sub n, like f sub n, any term, and divide by one term before, we will call that this is golden ratio. And it's always like 1.67. You can try, you can divide 3 by 2, 5 by 3, 13 by 8, 21 by 13, and so on. You will always get this. Okay, magic. Again, that means these numbers are used everywhere, even in the computer programming. Yes? And we have a couple of soft engineers in this classroom, future soft engineers. Okay. Okay, that's now I can show you nature. When you look at the trees, they actually growing like this. One, and then it's 2 branches, and then from that 2 branches, they will not both expand. Only one will expand, and then 2 will expand, because otherwise the tree will fall down. Will be not, yes, not, yeah, will be maybe too wide. Okay. Oh, that's my tree. Oh, that's another crazy tree. You can still find that pattern. Key of the piano, yes, 1, 2, 3, 5, 8, 13. Nature, you can also try to count these shapes. Okay, of course, human body has lots of ratios of following the Fibonacci sequence. And that's actually what I was saying. Oh, yes, 1.6, yeah, 67, 1.6 when we take these ratios. And this is also golden rectangle. Yeah. If you will draw a rectangle, you can even try. Just take a pencil and draw quickly the rectangle. And divide, yes, divide, this is A, this is B, divide, measure A length, measure B width, and get the answer. And the answer will be really close to 1.6. Golden ratio. That's how we are connected. Okay? And then architecture, of course. And yes, human body. Always, yes. Golden ratio, phi number. Okay. That's also beautiful picture. Okay. Nature. I just found lots of pictures. You may pause the video and look at these. Yes, look at these pictures everywhere. I'm not sure if this one, but yeah, some art. And even this one, yes, everybody knows The Starry Night by Van Gogh. Yeah. It's questionable that I don't know if that spirals will follow the Fibonacci, the golden ratio, but some of the mathematicians, they will really look, and I think you can even find the like the Python code to actually check this. Okay, yeah. But definitely this artist, Van Gogh, he didn't really think about like mathematically. He just did what he wanted to do for the picture to be beautiful. Okay, that's the Fibonacci sequence, Fibonacci numbers in like around us. And Pascal triangle I have. Oh, when you draw the Pascal triangle and these red lines that I draw, when you add these numbers, look at the sum. Fibonacci numbers everywhere, everywhere. Okay, that means now let's just finish the session with this exercise, because the next session will be about like the explicit formulas, and we will try to find the limit of the sequence. But let's just finish this introduction session with this. That's what we have. We have, of course, recursive definition. That means this is the recursive definition. This is the recursive definition. A sub n plus 1 is defined as a 1/2 times a sub n plus 2. And a sub 1 is given. We have to have always some given information, some additional. Okay, that means the first term is 3. And we have to find second one and the third one. Okay, that's we can see if this is 2, then this will be 1. Makes sense? If this is 2, because this one is 1 less. That means if this is 2, then the second term is defined first term plus 2. Okay, let's just substitute. 3 plus 2, 5. 5/2. Beautiful. And then the third term is defined 1/2 second term plus 2. And that's we can see we always need one term earlier, before. Okay, 5/2 plus 2. I don't know. Who can help me? 9/2, if I am not, because I did already add wrong 2 numbers for the Fibonacci sequence. Okay, that means that's it. That means please make sure that you can like understand the index, yes, the relation between a sub n plus 1, a sub n. And of course, if we would like to get 100th term, I will really need 99th. And if I need 99th, I mean computing 99th, I need 98th. That means this is a little bit maybe not helpful, but it's still, we can, if we ask computer, we can still get infinitely many of those terms. It's still good that we have this way of defining more complex patterns. But in the next video, we will actually focus on the explicit formulas, like a sub n will be defined in terms of n, and we will try to look how the patterns behaves as n goes to the infinity. Okay, that means that's everything for the introduction of the sequences. Thank you.